Hello friends, welcome to this video on Chernoff Bound. This video will let you know the formula to apply a Chernoff bound for a given condition and some application to problems where we can apply Chernoff bound and get the bounds for the given. Come on, let's get started. When the moment generating function of the random variable is known, we can obtain even more effective bounds on the probability what we want to estimate, namely z greater than or equal to a. So what is meant by a moment generating function? A moment generating function of a random variable x, which is defined by the quantity or denoted by the quantity mx of t, is expected value of the exponential power of tx. We define mgf mx of t as expected value of e to the power of tx. So when we apply a moment generating function, then the bounds which we get are called to be more effective, which means when compared to your Chernoff bound, the other bounds, namely your Chebyshev's or Markov, are going to be very weak in nature. So what's the basic idea of applying a Chernoff bound? Suppose we have a random variable x and we want to estimate the probability that x becomes much larger than its expected value. Expected value is its e of x. So instead of directly bounding z greater than or equal to a, what does Chernoff bound do is it exponentially transforms the variable. So when it exponentially transforms the variable, we will be able to apply the MGF to the random variable and then make it much more stronger to find the bound for any given value. Now we will get into the definition. If x is a random variable, then for any a belonging to the real number, we can write probability of x greater than or equal to a to be less than or equal to e to the power of minus at into mx of t for t greater than 0. So for positive values of t, what we have is x greater than or equal to a will be less than or equal to e power minus at into mx of t. This mx of t is nothing but our moment generating function. So we exponentially raise the variable and then apply it to the moment generating function, which makes the bound become more stronger in value. In the same way, when we have t to be less than 0, we have x less than or equal to a to be less than or equal to e power minus at mx of t. And so we see that the inequality is going to remain the same. What changes over here is t greater than 0 and t less than 0 with the bound greater than a and less than a. Now, how to make this one much more stronger? When we have the values of t to be greater than 0 as well as less than 0, minimize the function will help us to get a best bound for the data. So what we do is to the e power minus at into m of x, mx of t, that is your mgf, we are going to apply minimization. So when we minimize the function or the value of this function, then we will be getting our best bound. So the formula which you have to memorize for our Chernoff bound is given by probability of x greater than or equal to a is less than or equal to minimum of e power minus at into mx of t for the values of t greater than 0. So when t becomes less than 0, then what will happen? Greater than will become less than, but this inequality will remain to be the same. Come, let's apply it to problem and see how this works. Let Z be a standard normal variate with MGF mx of t equal to e power t square by 2. Using Chernoff bound, find an upper bound for z greater than or equal to 2, and we are also asked to compare it with one-sided Chebyshev's inequality. To begin with, by Chernoff bound, what we have is probability of x greater than or equal to a has to be less than or equal to minimum of e power minus at into mx of t, that is our moment generating function. So what the question asked is it greater than or equal to 2? So in place of a, I have it to be equal to 2. So this will be less than or equal to minimum of e power minus a is 2. So this becomes 2t. And what is our mx of t that has been given to us for the standard normal variate? It is e power t square divided by 2. So we have two values of exponential. we need to keep in mind e power a into e power b can be simplified as e power a plus b. So this will become minimum of e power t square by 2 minus 2t. Now our objective is to minimize this function. So we know or now notice that minimizing e power t square by 2 minus 2t is the same as we minimize t squared by 2 minus 2t. So we minimize this, then the quantity leads us to the same as minimizing this factor. Hence, what do we do now over here is we are fixing our f of t to be the value t squared by 2 minus 2t. Now, we are going to apply the constraints of maxima and minima, in which case we need the first derivative as well as the second derivative. Differentiate with respect to t square on differentiation is 2t divided by 2 minus 2t on differentiation is 2. So this is going to give me the value as t minus 2. And when I go for the second derivative, t on differentiation is going to be 1 and minus 2 constant on differentiation is 0. So we have this to be equal to 1, which is pretty greater than 0. And so we have the function f of t is going to be minimum. So our quantity is now guaranteed that it is going to be minimum. So the second derivative, if it is going to be greater than 0, then the function becomes minimum. And if it is going to be less than 0, the function becomes maximum. Keep this in mind. At which point does it minimum? The point at which it gets minimum is given by the first derivative equated to 0. So this gives us t minus 2 equal to 0, or at t equal to 2, it reaches the minimum value. So we will see what happens at the point t equal to 2. So go over here and substitute t equal to 2. So probability of z greater than or equal to 2, we have already minimized, so no need to write minimum one more time. This will be less than or equal to e power t square by 2. So this become e power 2 square divided by 2 minus, this is going to be minus 2t. So it is going to be 2 times of 2. So e power 4 by 2 minus 4. Okay, so this makes it as e power, this goes 2 times 2 minus 4. So e power minus 2. Use your calculators, we can get the value of e power minus 2 as 0.1353. So using our Chernoff bound, we have found Chernoff bounds. We have found that probability of z greater than or equal to 2 has to be less than or equal to 0.1353. So we are done with the first part. We have been asked to verify the same or compare with the one-sided Chebyshev's inequality. So let us move to the second part. So using your one-sided Chebyshev's inequality. What do we know? We have probability of x greater than or equal to c to be less than or equal to sigma square divided by sigma square by c square, and this will work when mean happens to be equal to 0. Do we have mean to be equal to 0? Yes, obviously. When z is a standard normal variate, what is going to follow? The mean is going to be 0 and the variance is going to be equal to 1. So n of 0, 1. So this pretty well guarantees that mean is 0. So I can directly apply for z greater than or equal to 2. So this will be less than or equal to sigma square value. For the standard normal variate, we see that the standard deviation or variance happens to be equal to 1. So this becomes 1 divided by 1 plus 2 square, which makes it as 1 divided by 5, and 1 by 5 is going to be 0.2. This is Chebyshev's inequality value. We notice that Chernoff gives 0.1353 and our Chebyshev's gives 0.2. We see that our Chernoff bound is going to give us more closer value than our Chebyshev's inequality. Okay, so this is the comparison which we get after applying the results. We will have one more problem to continue. Let x be a Poisson variate with parameter lambda equal to 2. Having MGF, mx of t is e power 2 into e power t minus 1. Use Chernoff bound to find an upper bound as well as compare the value obtained through Markov inequality. So we will first move on with Chernoff bound. Chernoff bounds is given by probability of x greater than or equal to a is less than or equal to minimum of e power minus at into mx of t. Now what we require is going to be probability of x greater than or equal to 3. This will be less than or equal to minimum of e power minus 3t, and mx of t can be resubstituted from over here 2 into e power t minus 1. Now this can be combined and we will have it to be written as minimum of e power 2 e power t minus 2 and minus 3t. Now minimizing this is the same as minimizing e power 2t 2 e power t minus 2 minus 3t is same as minimizing 2 e power t minus 2 minus 3t. So let us take this to be our function f of t, in which case our f of t is 2 e power t minus 2 minus 3t. We will have to show that it is minimum. So we need the first derivative as well as the second derivative. 2 e power t on differentiation is 2 e power t minus 2 0 and minus 3t gives me minus 3. Second derivative is 2 e power t and this will become 0. E power t is obviously lying between 2 and 3 and so this value is obviously greater than 1. So this shows that the function f of t is minimum. So whenever it works in the opposite way, value is greater than 1, it becomes minimum. Okay, so where is the point where it becomes minimum? So it will be given by f dash of t equal to 0. So we have 2 e power t minus 3 to be equal to 0. So we have e power t to be 3 divided by 2. So at this point, the function reaches the minimum value. Let's go and resubstitute it back in the given function. So what happens if we are going to substitute over here? Probability of x greater than or equal to 3 is less than or equal to e to the power of minimum we drop because we have already minimized it. So e power 3t e power minus 3 times of t, and then you have it to be 2 e power 2 into e power t minus 1. So this is the value which we have. So let us take this as e power t the whole power minus 3 e to the power of 2, and this e power t can now be replaced with 3 by 2 minus 1. Now this gets replaced as 3 by 2 whole power minus 3 e to the power of, this makes it as 2 and 2 cancels off. So this makes it as 3 minus 2. Now since this is minus 3, you flip it. So this becomes 2 cube divided by 3 cube into e to the power of 3 minus 2 makes it as 1. So the value now taken is 8e divided by 27. You can use your calculators to estimate the values of e, and then we find that the value of 8e by 27 leads us to 0.8054. So we are done with Chernoff. The second part which we have is to compare with the Markov inequality. So when we compare it with the Markov inequality, what we know about Markov's inequality is that probability of x greater than or equal to a is less than or equal to e of x divided by a. So we want probability of x to be greater than or equal to, the question asks for greater than or equal to 3. So greater than or equal to 3 is less than or equal to e of x divided by 3. What is this e of x now for us? What is the distribution we are dealing with? We are dealing with Poisson distribution with parameter lambda equal to 2. When parameter is 2, then the mean of the Poisson variate is the same as your parameter. So this is the same as our 2. So this will be equal to 2 divided by 3. And so this leads us to the answer 0.666666. Okay, so this is the answer which we get through Markov, and the value which we get through Chernoff is 0.8054. Which you think is going to be more closer? Now we see that Markov is providing us a closer solution than Chernoff. But why is this happening? When we started, we see that what we had over here is the estimate the probability of x becomes much larger than its expected value. So if you have a value which is going to be greater than the expected value, then you can find the Chernoff to give you a closer value or an appropriate value. What happens over here is we have x to be estimated for greater than or equal to 3, and the value of our mean is going to be equal to 2, which is very close to the value of mean. So since the Chernoff's value of A is very closer to mean, we see that the bounds obtained through it will not be as powerful as the case when A is going to be more than that of its mean. Okay, so when A turns out to be a bigger number, maybe Chernoff will give us a more accurate answer than the Markov. And since the value of 3 is very closer to 2, we observe that Markov is giving us a better answer than the Chernoff. So there are going to be certain deviations like this on and off over here. But if you are going to apply the process correctly, we will be able to find a more appropriate answer to the unknown probabilities which we have in Happy Learning. Keep learning.